So in the last section, we saw that there is a relatively fast approach to find an Eulerian cycle in a network that has it. And at the same time, if a network is not connected and balanced, we can quickly say that we know that that network does not have an Eulerian cycle. Now, you may be wondering, what's the big deal though? Why do we need to care about these issues? Because I thought computers were super machines. Should they really need this 300-year-old math stuff to solve problems in everyday life? Aren't they really going to wind up taking over the world anyway? Well, I mentioned the Eulerian cycle problem. I didn't say anything about Hamiltonian cycle. And if we look at the case of solving that problem, the key point there is that no one has ever found a similar efficient test of whether a network has a Hamiltonian cycle or not. That would correspond to Euler's theorem. That gives us a fast way of either finding a Hamiltonian cycle or proving definitively that the graph or the network does not have one. So we could, of course, just simulate the process of having many different ants walking through the network. So we could essentially examine every possible walk through the network in order to solve the Hamiltonian cycle problem and say, if any ant is able to walk through the entire network using every node exactly once and coming back to its starting point, then we save that Hamiltonian cycle and say we're done. And then if all the ants try every possible walk through the network and none of them is able to find one, then we can definitively say no. But we have to make sure that the ants try every possibility. But that approach, which we might call brute force, winds up being infeasible. And the reason is because there are more walks through the typical network with just 1,000 nodes in it than there are atoms in the universe. So as soon as we go to a larger network, this might work for a small network, but as soon as we go to a larger network, this idea simply won't work because there are just too many possibilities to consider. It doesn't matter how fast our computer is. There are too many possibilities to consider, essentially. So, in other words, attempting to solve this Hamiltonian cycle problem is very difficult because no one's been able to find it. But if your boss had asked you to do it, you might go to them and say, well, I guess I'm just too dumb. And this is from a classic series of cartoons from 40 years ago. So the hope is that you could go back to your boss and say, I can verify that I failed. I couldn't find a Hamiltonian cycle problem solution because there just isn't an efficient method. I can verify to you that there isn't one. But the present state of affairs is that a lot of really intelligent people have tried to solve this, but no one has ever been able to find that efficient test for solving the Hamiltonian cycle problem. And that is such a fundamental question that it's actually been added to, it was added to a list of 7 millennium problems by the Clay Institute in Massachusetts. They said, if anyone is able to find an efficient algorithm for this Hamiltonian cycle problem, or demonstrate definitively that there is no efficient algorithm that can be used for, say, large networks, then they will award you a $1 million prize. So this was one of 7 different problems that were announced in 2000. And thus far, only one of these 7 problems has actually been solved by Grigory Perelman, a Russian mathematician who turned down the prize, actually. So one of those 7 problems has been solved. The Hamiltonian cycle problem is very much unsolved. And no one knows still whether there is an efficient way of solving this problem. So keep this in mind, that we have one problem with an efficient solution to it, which is finding an Eulerian cycle or proving that there isn't one. We have one that has no known fast solution, which is finding a Hamiltonian cycle or proving that there isn't one. And the divide in those 2 problems is going to wind up being very important. So we're going to come all the way back to the biological problem at hand in the next section.